to the Gordon Current Science and Technology stage here at the Museum of Science. My name is Kai, I use he, him pronouns, and I'm one of many educators here at the Museum of Science. But we're not here to talk about me. You are here to listen to Dana Maloney, who is an electrical engineer at Boston Dynamics, and he's going to tell us about the daily life, tools, and joys of a robotics electrical engineer. Please join me in welcoming him to the stage.
Hey everyone, good afternoon. My name is Dana Maloney. I'm an electrical engineer at Boston Dynamics over in Waltham, Massachusetts, and thanks for coming to listen to me talk today. So, quick overview of what I'm going to be talking about, just a little intro of myself and who I am. We're going to go into what an electrical engineer actually does, as well as a day in the office, like what my day-to-day looks like. And then after that, I'm going to talk about how you can get into your dream career, whether that's engineering or a different field as well, and then I'll open it up for questions. So a little bit about myself. I'm from Shirley, Massachusetts, which is about like an hour or so away. Anyone else from around there? Yeah, nice. I started there, then I moved to Lowell and went to UMass Lowell to get my degree. Now I work at Boston Dynamics, and outside of work, I like working on cars, running, fixing old electronics, and I play on a soccer team here in Boston. So what does Boston Dynamics do, right? So you know about me, this is where I work. And what we do is we try to imagine and create exceptional robots that enrich people's lives. So there's a lot of big words there, so let's break it down really quick, right? So to imagine and create robots is we're inventing new ones, right? Exceptional means that we're above the norm or different from what's out there. So these are all new robots that do things that maybe other ones don't yet. And to enrich people's lives means to help them. So we have our 3 different robots up there. There's Spot, Stretch, and Atlas. You guys might have seen Spot on America's Got Talent. You might have seen it in the museum over there. And what it does is it can look around and find things that are wrong in factories. It can go in dangerous places, and it helps kind of keep people out of situations where they might not want to be in case they get hurt. We also have Stretch, which can move heavy boxes in warehouses and kind of keep people from lifting up those heavy objects. And then we have Atlas, which is a research robot. So it doesn't really do anything super helpful right now, but we make it to see kind of what we can do with robotics and how far we can push a robot and see what it can do. So that's what Boston Dynamics does, but I'm also here to talk about what I do. So as an electrical engineer, do you guys have any ideas of what an electrical engineer does, maybe what I work with? And if you raise hands, I have some Spot stickers up here that I can give out to participants. Any ideas? All right, well, all good. We can talk about it. So here's some of the parts, tools, and skills that I work with or use in my day-to-day, right? So for parts I work on, it's pretty much anything that electricity flows through. So this includes circuit boards, which are what make up all of our electronic devices. There's one inside your phone. If you have a game console, there's circuit boards in there. Then we have the wires and wiring harnesses that connect all of the boards together, and the connectors that go in between them. So I work with designing all of these things and testing out parts to make sure that they'll work inside of our robots. For tools I use, there's quite a variety. For electrical engineering design, we use a lot of design and simulation software on a computer. So if you've ever played like Minecraft and you use Redstone, right? It's very similar to that. We draw it out and we test it and we make sure everything works. The specific software I use is called Altium. For hardware tools, I use a soldering iron to connect electronics, and that's kind of like hot glue that sticks everything together. So if you have like little chips in a device and they have to stick on the board, we'll use a soldering iron to stick them on. And then as well as that, I use some other tools like a multimeter and an oscilloscope to make sure that we can see how electricity is flowing through a board and if signals are coming through the way that they should. And finally, I also use a computer terminal. So for that, it's basically me typing into a little box on the computer and sending commands to robots or to chips to make sure that they respond the way we expect. And then some skills I use, there's soldering, which is like I was saying with the soldering iron, making sure that we get parts onto boards. Sometimes if something doesn't work, I'll have to take it apart and put a different part on in its place. And to do that, you'll need to be good at soldering. Also circuit theory, for those of you who are in college or in your undergrad, if you're taking an electrical or computer engineering degree, this is like the most important part, the bread and butter. Circuit theory courses will be your fundamentals as an electrical engineer. It also helps to know how to program. If you're able to write some scripts that can turn power supplies on and off, or maybe automate a test, it can help make your job easier. And finally, written and spoken communication, kind of like me being here right now. And I'll talk more about why that's important as an engineer towards the end. So as an electrical engineer in robotics, there's really two big parts to my job, and those are sustaining work and designing work. So to start, sustaining work is working on older parts, or things that already exist. So we've been making Spot for a while, right? In order to keep Spot running, we want to always make sure that the parts are being made the best way possible, the quality is good, and we're going to fix and improve upon our older designs. And then the other part of it is failure analysis. So if we make a lot of them, sometimes one might not work, and we'll have to look into why and figure out a corrective action for it before we send it out to the customer or out into the field. And then the other half of it is design work. So this is working on new things that aren't out yet, or things that don't exist until we take the time to develop them. This includes designing new parts and testing those new parts and products before we send them out into the world and kind of make them for everyone. So here's a little bit of a day in the office for me. This is an example of some sustaining work. So here's a fake circuit board. This is the thingy right here. And let's say at Boston Dynamics, right? We've been making the thingy for like 5 years. Same parts, same recipe, nothing changes. And here's a breakdown of the parts in there. So we have like a computer chip, we have capacitors, resistors, and light, and you need all of these parts to make it. Now, one day, one of the companies that makes those parts stops making it, right? So that's gone. And we can't make the product if we don't have all the parts that go into it. So as a sustaining electrical engineer, I'll need to go and find some new substitutes that we can put in its place to keep making the product. So you can see there's a couple of example replacement parts for a chip there. So we'll have to go in and read the data sheets. We'll need to maybe get the parts in and test them and see how they work, right? So I start by testing part A, and we put it on the board and it gets way too hot when it's running. So this wouldn't work out for us because we don't want to send something out or produce something that doesn't work within the environment we want it in. So I wouldn't use part A. Part B works fine, but it's too tall to fit on the board. So we wouldn't be able to use this one in production either. But then, we keep looking, and the third one, part C, works just right. It fits, it works in the environment, and if it checks all the boxes, then we'll move forwards and put it onto the board and keep making it. So now you can see we have the thingy version 2. And keeps going. Now the other part of sustaining is we make a lot of these. We'll make a large volume of products. So in this case, right, maybe 10 of them at the factory one day, the light doesn't work on the thingy. So as a sustaining engineer, you'll get called in and you'll go to look at what the issue is on the factory floor. What's the problem and what's causing it? And then from there, I'll try to reproduce the failure. So I'll take one that does work and try to make it not work in the same way as the other ones so that we can confirm we know what the failure is. And then from there, we'll try to figure out a corrective action. How can we stop this from failing in the future and keep making the part the way that we want? So that's a little bit of sustaining work. The other half is design work. So this is designing new parts and things that maybe don't exist yet or things that aren't on the market. And if we're working on that, we might want to come up with some cool ideas that go on Spot. So let's say maybe we're going to make a new attachment that can do something cool, like an arm or some kind of accessory, right? So to do that, first we have to come up with the idea and figure out how it works from an electrical perspective. So maybe we'll draw out something that says like, oh, we need these parts to make a circuit that will do the thing that we want, right? So once we have our concept, we'll put it into that design software I was talking about earlier. In our case, it's called Altium. So I basically took my drawing and I recreated it on a computer, and I tell it what parts I want to use in said drawing. So from there, we can simulate the circuit, which is basically just like a test run on the computer without buying any of the parts yet to see like, will it work in theory, right? If we say everything's perfect, will the part work? And if the answer is yes, then we'll go ahead and start designing what that would look like on a circuit board. So what you're looking at here on the right with this drawing is what the layout of a circuit board looks like before we actually make it. So the red stuff is basically wires connecting the parts, and those yellow outlines are showing where the parts would go on the board. From there, right, we can get a 3D model, see what it looks like, make sure it'll fit into a robot or into wherever we're putting it. And then once it checks all the boxes and everything looks good, we'll actually order it, and we'll send the design to a factory to get it made. So once we get the boards in the mail, we'll take them to the lab and we'll run some tests to see if everything works the way we expect. Will it work in a hot environment? Will it work in a cold environment? Does it work if we give it too much power or not enough? And we put these through a lot of crazy tests. We also do like shock and vibration, where we'll basically slam them using a machine with like 100 Gs or some really high force to make sure that they don't break if it drops or if a robot falls. Because right, you saw Spot earlier, you can walk around in dangerous places. Sometimes those robots will fall down stairs and they'll slip because they'll be on uneven terrain, and we have to make sure that they can get back up and keep going after. So that is what the design side of working in electrical engineering looks like. And then the third part is working with a team. So if you've been in school, you might have had to do some group projects or work with your friends. And I hope that you like doing group projects, because engineering is basically a career of different group projects. So you're gonna have to meet with all sorts of different people to get your design into a product. And this includes other engineers who you're gonna wanna have check your work. It's really hard to make a complicated circuit board by yourself because you might make a mistake. So you'll meet with other engineers to make sure that your design is actually gonna work and is functional and doesn't have any problems. You're also gonna meet with other engineers on different teams, like mechanical, to make sure that your board fits in the robot and make sure that all of the connectors are in the right place and things like that. And then on top of that, you're also going to meet with people in sales and business who are going to make sure that we can buy enough parts to make enough of the pieces to go into all the robots, as well as sales to make sure that, you know, what we're making is what people want. So there's a lot of different communication involved in robotics and engineering. And then the other part of that too is, as an engineer, you're doing a lot of really technical work. You're making complicated things, and they might be hard to understand for someone who didn't do that work, right? So you need to be a good communicator so that you can take really complex topics and break them down for other teams and for other people on your team who may not be familiar. So if this sounds of interest to you, right, you might be wondering how you could get into an engineering career. And there's different steps you can take at any point in your life. You could be in elementary school, in middle school, in college, and there's always something you can do to kind of learn a little bit more, or to make yourself, if you're looking for a job, you know, make yourself more appealing as an applicant. So starting in grade school, it's really good to kind of get into some hobby kits and activities. It's never too early. So you could look for, if you're in engineering, you could maybe try going on Scratch. It's like a programming website, and learn the basics. You program with blocks, and it tells characters how to move. You could build with Lego Robotics and start to kind of like figure out how to make things move and how things work. And then another thing you can do too is just take things apart with permission. Do not take things apart without your parents' permission. But if you want to see how something works, you can take it apart and see what's wrong, especially if it's broken. You can even try to fix it and see if you can get it working again. And then finally, youth clubs are also a really good way to get involved. So for elementary schoolers, there's usually STEM programs like First Lego League, which is a Lego Robotics competition. And you can get involved in those to kind of get a little bit of a feel for if it's something you're interested in, and also learn about how to make a robot. For middle school, same thing. There's also competitions like Vex Robotics and First Tech Challenge and things like that. And if you're not into engineering, this also applies to other places. You can always look for clubs of your interest, and you can always find other hobby kits that aren't related to engineering as well. In high school, after-school clubs and organizations can be really important. First Robotics is one that I was in, and it really helped me kind of like learn my love for robotics and get involved. And personal projects are something you can do as well. Things like Arduino and programming websites and things like that can kind of help you start to build up a little bit of a repertoire and like a portfolio of projects for things that you're interested in. In college, again, joining clubs is super important. I joined my school's Riverhawk racing team, which is like, we build and race a race car every year, and there's a lot more electronics than you might expect to go into that. So that was a place where I was able to kind of build up a little bit of a project portfolio to talk about when applying to jobs. And even if you're not in school and you're still looking to maybe get into a career that you're not familiar with, or one that you're trying to apply to a lot of jobs in, networking can be really, really key. Getting friends in industries and being able to talk to them, learn what people are looking for and what skills are wanted, can be like really, really important for just having a pulse on what people want. And as well as that, personal projects are always an option. If you find something that maybe would make your life easier, or something that you think would be cool that you could share online, go ahead and try to make it. The worst thing that can happen if you fail is that you'll learn something and you can keep going and iterating from there. So here's how I got into robotics personally. For me, in grade school, I was always tinkering. I was trying to like make different devices and electronics. One of my favorite projects was I tried to make an arcade machine using an old laptop and like kit from eBay that had like a little controller board. So I cut up like a bunch of wood, like put all the buttons in and fit it around the laptop. And that was a fun project. As well as that, Scratch programming was a really important one for me. And you're able to just like kind of get the fundamentals of programming without looking at something really scary and intimidating. Like text-based programming can be a lot if you haven't done it before. So Scratch is a good way to get started. And then finally, Arduino projects. For those of you who aren't familiar, Arduino is a small like project board that you can program in C on, and you can use it to control motors and lights and all sorts of other devices. And as well as that, you can connect it to other things through communication platforms, so you can hook up motor controllers and speakers and other more complicated things. So if you want to do a basic robotics project, an Arduino can be a really good place to start. And then in high school, I kept going with some more personal projects based on Arduinos and Raspberry Pis. And I also went into FIRST Robotics, which was honestly, I think, the most important like piece of, or stepping stone, I guess, on my way into a career in engineering. So with FIRST Robotics, you again have 1 year to build a robot from scratch, and then you go compete against other high schools up to a national and even international level. And you can learn a lot from it because there's good mentors there, and there's also a lot of other really smart students who are willing to share their ideas and collaborate. And then in college, I kept the tinkering going by working on cars. I had a Volvo, you can see the picture there, that I used to work on like all the time because I always had a problem. But through it, I was able to learn a lot about kind of mechanical structures and also about wiring on an automotive grade project, because cars go through hot weather, cold weather, water, and building something that can last through all that is actually pretty tough. And finally, internships. So if you are in college and you're looking to get into a field as you graduate, internships I think are more important than ever right now. It puts you ahead of other candidates because you're going to come out of a degree with maybe 3 months, 6 months, a year of experience in the industry, and other candidates may not have that. And as well as that, it also shows that you're capable because you've already kind of worked in a full-time job, so to speak, through your internship. And the last part of that is internships are really useful because you can find what you do and don't like. I worked at a couple of other companies before Boston Dynamics through internships, and I was able to find what team dynamics I liked and didn't like, as well as what pace of work I liked and didn't like. So for me, I was able to find out that I liked fast-paced work in a group versus maybe something more individual and alone. So that is my little path through engineering. And at this point, if you guys have any questions, feel free to ask.
Thank you so much, Dana. That was super interesting. Like Dana said, now is the time to ask questions. We have a couple minutes for questions. Does anyone have a question they want to ask? I have a question that I want to ask. I think it's really cool that you've worked so much on cars. Do you think there are important similarities between cars and robots that help you do your job?
I would say absolutely, right? Both cars and robots are machines with electronics that kind of have to, well, a robot is something that can think and act and feel, right? And a car has to do something similar, right? Cars have to think about when to basically inject gas, when to blow it up. They have to be able to sense where the engine is to know when to do that. And it's there's a lot of similarities, both in terms of like what they do and also in terms of kind of like what parts go into them. There's actually a lot of overlap between the two industries. So I would say it's a lot of common ground.
Any questions? We have time for, yeah.
Well, I happen to know that your degree was actually in computer engineering, and so I thought it might be helpful if you told people a little bit, the fact that you don't necessarily have to, start out in a particular field like electrical engineering and be able to get into that field.
That's a really good point. So for those who couldn't hear the question, was basically my degree was in computer engineering, right? But my job is as an electrical engineer, and those are not exactly the same thing, right? So it is true, you don't have to necessarily go directly into what your degree was about in school. You can kind of like broaden and find what you really want and go with what you want to do in your life. You're gonna have to go to your job 5 days a week. You want to go to something that you enjoy. And for me, I found out that I really liked electrical engineering and working with hardware. So I was able to kind of steer towards that through internships a little bit, even though I was going to school for computer engineering and more digital systems design and things like that. Through internships, I was able to do hardware tests and kind of like get more involved on the side of like hardware design and validation. And yeah, it's never too late to go into something like that. If you can build up the skills and show that you're either a fast learner or maybe you have a passion for something outside of your degree, jobs are willing to hear that and look at the skills that you bring to the table. And you can move that way as well. that's just going with what your degree actually was offering.
I think we have time for another question. Does anyone? Yes.
What kind of emerging technologies you see having a great impact in the field of robotics in the next few years? Like, whether it is AI, quantum computing, like any emerging technology that you see right now.
It's a good question. So, like emerging technologies in robotics right now, I think a really big one is like high-speed networking and things like that. Right? We have robots that we want to do very complicated tasks, and to do that, you need to have them know a lot about where they are. So, high-speed networking and good sensors and things like that, I think, are really crucial to robotics right now. And those are things that, if you want to have a robot that can handle a complicated environment that maybe it wasn't designed for, it's going to need to know how to handle that.
Thank you again. Can we give another round of applause for our speaker? If you would like to come up and ask a question of Dana one-on-one, feel free to do that. If you'd like to see Spot is over there. And if you would like to join us for the AI and Tech Careers panel, that's going to be in the green wing lower level at the Science Live stage at 1:30. So feel free to head right on over there if that is something you are interested in. Thank you again. Have a great rest of your day at the Museum of Science.